In this video, we introduce our paper UniDet3D, Multi-dataset Indoor 3D Object Detection. Growing customer demand for smart solutions in robotics and augmented reality has attracted considerable attention to 3D object detection from point clouds. Yet, existing indoor datasets taken individually are too small and limited to train a powerful and general 3D object detection model. State-of-the-art 3D accuracy in indoor benchmarks is achieved with the standard training on categorical labels, which produces dataset-specific models. Unfortunately, general approaches based on foundation models still cannot beat supervised methods. Can we tackle all 3D indoor datasets with a single unified approach? In this work, we propose UniDet3D, a simple yet effective 3D object detection model, which is accurate and general at the same time. Trained on a mixture of indoor datasets, it generalizes to various indoor environments and sets new state-of-the-art in 6 indoor benchmarks. UniDet3D is a transformer-based method, which is no surprise, since transformers has dominated 3D object detection over the last years. Existing transformer methods first extract point cloud features with a sparse convolutional backbone. Then, they predict objects from input queries with a transformer decoder through cross-attention to the backbone features. They also use computationally extensive Hungarian matching to assign predicted bounding boxes to ground truth ones during the training. Overall, a decent part of progress in transformer-based 3D object detection is attributed to sophisticated architectures, elaborated positional encoding, and non-trivial interaction between modules. On the contrary, we use a simple self-attention encoder architecture without positional encoding and cross-attention. Since our superpoint-induced query initialization strategy preserves spatial information, there is no need for adding positional encoding. Apart from that, UniDet3D query initialization allows using the efficient disentangled matching instead of costly Hungarian matching. As can be seen, UniDet3D, trained without positional encoding and Hungarian matching, achieves the highest detection accuracy on ScanNet among transformer-based methods. Removing positional encoding reduces time and memory footprint, so we can claim both these transformer-specific parts to be redundant, which is a valuable insight. But how we do it? Let's take a closer look at the pipeline. Given a point cloud, a sparse 3D UNet network extracts pointwise features. In parallel, superpoints are obtained through unsupervised clustering. Then, point features are aggregated within each superpoint by simple averaging. It is referred to as superpoint pooling, which gives superpoint features. Superpoint features are passed as queries to a vanilla transformer encoder. The encoder outputs are processed with 2 separate MLPs. One estimates class probabilities in multi-dataset shared label space, and another one predicts regression parameters of objects bounding boxes. Another issue we need to address when training on multiple datasets with non-unified annotations is how to handle heterogeneous label spaces. We refer to the original non-unified label space of different datasets as to a separate label space. The partition scheme implies merging identical labels across datasets, but still using a separate classification head for each dataset. UniDet3D follows the third scheme, which we call a unified scheme. Unified label space is the same deduplicated set of labels during both the training and inference. Our experiments show that the unified scheme supersedes the partitioned one, not only in simplicity, interpretability, and fewer training parameters, but also in accuracy. In our first series of experiments, we compare UniDet3D with single dataset state-of-the-art methods. The best results for ScanNet are achieved with VDETR, while MLCVNet report the highest accuracy for ARKit scenes. and TR3D is the top-performing approach on S3D-IS. Our UniDet3D outperforms all of them when trained jointly using unified label space. For S3D-IS, the accuracy gain comprises impressive plus 9.1 MAP at 50. So, for these three common indoor benchmarks, UniDet3D establishes new state-of-the-art. To obtain reference values for smaller and less-known datasets, Multi-scan, 3R-scan, and ScanNet++, we train and evaluate FCAF3D and TR3D, two solid baselines with open-source code. The observed improvement over these methods is especially tangible for multi-scan, where the difference is 7.5 of MAP at 25 and 9.3 of MAP at 50 in favor of UniDet3D. Therefore, UniDet3D achieves the best quality in 6 indoor benchmarks simultaneously, without being retrained or fine-tuned to better match a specific domain. The benefits of joint training are fully revealed for small datasets, and the difference between partitioned and unified label spaces becomes more expressed. Unifying label space improves the overall quality over the partitioned label space and brings 1.7 MAP at 50 on S3D-IS. Taking the better interpretability of unified classes and the smaller size of the classification layer, 99 unified classes against 159 in the partitioned label space, we can claim the unified label space as a preferred option. Not only is this an interesting experimental finding, but a useful feature for real-world applications. To round up, we proposed UniDet3D, a 3D object detection model trained on a mixture of indoor datasets. By unifying label spaces across datasets in the supervised joint training scheme, UniDet3D generalizes to various indoor environments. The network architecture of the proposed method is built upon a vanilla transformer encoder, making the entire pipeline easy to use and adapt to user requirements. Extensive experiments prove UniDet3D to deliver state-of-the-art results in 6 indoor benchmarks: ScanNet, AR-kit scenes, S3D-IS, Multi-scan, 3R-scan, and ScanNet++. Thanks for your attention.